Hello, this is number 20, Christmas tree lecture number 20. I doubt if anybody here except me has been here for all of the previous 19. But the basic idea is that one of the most important things to computer scientists is trees. And every year I learn at least one really cool thing about trees that I didn't know before. And so every year I give a Christmas tree lecture in which I try to explain this as well as I can. And wow, have I got something to tell you guys tonight. It's always most fun to give a lecture when you know that you got a great story, so I'm going to get right into it. But I'm going to try to get into it slowly so it's not too scary. Now, we're going to talk a lot about numbers tonight, and I thought, by the time I got 76 years old, I would probably have seen all the really amazing, fairly simple patterns of numbers. But I was really surprised, and I'm going to show you some new stuff that blew my mind during the summer. Well, I guess it was more like October when I came across these things. Now, I'm not the only person in the world who knows these things. However, it was new to me, and so I was going to explain it to you. I have a few new things to say. I think maybe two. And in order to check out what I do, I'm going to be using computers, so you can check the numbers. Isn't that good? And so I worked out a set of function definitions for Mathematica, which I'm going to put online, and it's called. I mean, you won't have to memorize these, but I just want to show you that it exists. So this is going to be online. You'll be able to download it tonight, and so it's called Christmas20.m, and there'll be a link to it. So these are a bunch of programs that'll make Mathematica compute the kind of stuff that I'm going to be talking about. Now, okay, this is too small to read, of course, but I just want to show you that it exists. Now, here, however, I'm going to zoom in on stuff, and so here. And can you try to get as large as you can on this part here? Okay, a little bit. Oh, actually, it shows better on that screen than on my screen. Okay, so here I'm using this this proprietary program here, and I first set it up so that the be possible to zoom in without going off the screen. So you can go, yeah, oops, that. Okay. Here we're doing. So at the beginning, that set options just make sure that I'm not going to make the lines too wide. Now, then the next thing is I input this file Christmas20.m, and if you look at the bottom of the file, actually, the last line of the file is Merry Christmas. Bill Gosper got the joke. When it inputs a file, it always displays the value of the expression on the last line of the file. But Merry Christmas is the product of two variables, Merry and Christmas, and it always reorders them in alphabetical order. So we have, so anyway, now that's my joke for the night. Next line is B210. What do I mean by that? Okay, so now I got to tell you the story. This whole idea of trees is not only important in computer science, it's really important in my life. I mean, it changed my life when I was a sophomore. When my teacher gave me a challenge problem. It turned out the solution to the problem was to find the generating function, or to find the Catalan numbers. And the Catalan numbers are now so famous, but it's a number of binary trees that there are with n nodes. What's a binary tree? A binary tree is either empty, or it has a root and then a left binary tree and a right binary tree. So a root and two binary trees, or empty. the Catalan numbers are the number of binary trees with n nodes, and the coefficient of z. Those people in Canada will realize that I don't say z, I say z. This is so B2 is the function for trees, binary trees. B3 will be ternary trees. And 10 says just give me up until order z to the 10th. So here the coefficients up, they infinite series, but up until z to the 9th, I've got the numbers there. The number of 9-node binary trees is 4962 or 4862, and you see there's one binary tree with one node. It's just a root, and then there were 2 with 2 nodes and 5 with 3 nodes, and so on. Those numbers are some of the most important numbers to me in my life, just because I've encountered them zillions of times. Okay, now in my book Concrete Mathematics, I have what I call a generalized binomial series, which includes not only the binary trees but also the ternary trees for all t. And so that's on page 200 of Concrete Math, and we got, let me see, can you go down to where I'm pointing? Yeah, here we go. Okay, generalized binomial series, and it's defined by this formula here. So I call it script b sub t of z, and that's the one, when you put t equals 2, that's the one that we got for the Catalan numbers. And here it is a basic identity that defines this for any t. It's sort of a polynomial equation when t is a negative integer. But anyway, this is the main equation. And then on a couple pages later, I show you the Catalan numbers. And so you see there's a simple formula for the coefficient of z to the k. That's the Catalan number. And there's a lot of other things going on, but one of the really great formulas is actually on the previous page, where it shows that if you have any t whatsoever and any power, there's a simple formula for the coefficient. So if I have 8 airy trees or something, and I want to cube it, then I just take t equal 8 and r equal 3, and I plug in, and I get the number of ways there are to have 3 octenary trees. So that's Concrete Math, generalized binomial series, and that's one of the most used pages in my copy of the book. So now, next thing on the transcript here is B3(9). This shows ternary trees. So a ternary tree is the same thing. It's either empty or it has a root, and then 3 ternary trees. And so these numbers go 1, 3, 12, 55, 273, 14, 28. Now, I don't know those numbers quite as well as the Catalan numbers, but tonight, I urge you to remember them, think about them. These are going to be great numbers for tonight. 1, 3, 12, 55, 273. That's far enough. But anyway, you see a number 55. That's pretty easy. The speed limit, and so on. Okay. Now, so that's ternary trees. And last year, my lecture was about ternary trees, a special kind of ternary trees in the connection with geometry. The basic property of the ternary tree function, which I can call t of z, let's say, this is script b3 of z, and t of z, it's equal to 1 plus z times t of z cubed. And this generating function says that it's either an empty case, which means there's no nodes, and that's why I get this 1 in here. Or there's a root node, which I call Z, and 3 other ternary trees, and that's why t cubed accounts for 3 other ternary trees. And so the solution to this equation is a series in Z that defines ternary trees. Now, whenever I learn a concept in math, I try not only to generalize upward, but to generalize downward. I don't know, not every mathematician believes in this, but I always like to, I mean, when I learned two-dimensional geometry and three-dimensional geometry, actually, no, I think I went to four-dimensional geometry, but then I said, wait a minute, let me learn one-dimensional geometry and zero-dimensional geometry. What is that? You know, what I know what the volume of a sphere is, and in 4 dimensions I knew what it was. But what is the volume of a sphere in 1 dimension? You know, and so I had to see what the formulas were. So anyway, let's look at B1. You know, B1 of Z. These are unary trees, right? That's 1 plus Z times B1 times B1 of Z. And so that's B, it's the solution to Z, B equals 1 plus ZB. So that's an easy one to solve. And you see that the power series is pretty easy. Oh yeah, zoom in on that. Zoom in on the computer output for me there. Okay, so here we got, you know, there's just one unary tree of 10 nodes. It's got a root, and then it's got another unary tree of size 9 below that. Okay, and then of course you got to go further too, and then go to B0. What are the nullary trees? And these are it's either empty or it has a root and nothing below it. And so it's 1 plus Z, and then I went up here to big O of Z to the 100th. I could have gone up to 1,000, but I didn't want Mathematica to compute too hard on this. Okay, now, so anyway, you can try other values, and the title of my talk tonight is 3 halves-ary trees, and this is, so B3 halves. And here I'm going up to Z to the 9th, and you see, that it's 1 plus Z, then there's 3 halves with 2 nodes, and there's 21/8 with 3 nodes, and 5 with 4 nodes, it turns out. Well, we have to figure out what it means to be half a tree. But anyway, the formula gives us this, and because I showed you that no matter what T was, there was a simple formula for it using binomial coefficients, and even the simple formula raised to a power, at least we got a number here. Okay, so lots of formulas give numbers, but if they aren't integers, it's hard to interpret what they mean. And so we got to look a little further. But as long as we're generalizing, let's try pi. Why not? And so let's try pi-ary trees. Okay, and so it's 1 plus Z plus pi Z squared, and then here's minus pi over 2 plus 3 pi squared over 2, and so on. And finally, when you get into later terms here, it explains it. It gives it directly in terms of binomials, so that you can see it didn't even bother to evaluate what this was, because it would be harder in other formulas. So in other words, just if you plug in T for pi, that's what you get. Here I tried I, imaginary square root of -1, and so I have no idea if this formula has any use whatsoever. But if it does, I propose that we call them imaginary trees. Okay. Now, okay. So I also want to show you ternary trees squared. Here I went only to 8 terms because otherwise it would take another line. And here, there's another set of numbers that, to keep in mind tonight, because we're going to run into this number, these two again. So this is 1, 2, 7, 30, 143, and so on. Now, this is the number of ways that you can have a pair of ternary trees, an ordered pair of ternary trees. And so it's a square of that generating function. And here I just calculate binomial coefficients according to the formula in concrete math, and lo and behold, I get the same numbers: 1, 2, 7, 30, 143, 728. Okay, so this I got it not only in this case I got it by squaring a series, and here I got it by plugging into another formula. So at least it gives some evidence that that formula works, and it works for any power. So I change 2 to any number here in all 3 places in this formula, and that would give me the any numberth power of that thing. Okay, now why are the 3/2 case so interesting? And I'm going to show you a little bit first. Let's take the 3/2, the generating function b 3/2, and take the square root of that function. So this means I'm not going to have, when I squared it, I had two trees, but here I have the square root, which says sort of I have something like half a tree in some ways. If I multiply this by itself, I have an ordered pair of half trees, and that gives me a full tree. And so, a 3/2 area tree is supposed to be a root and 1.5 other 3/2 area trees below it. So what does a half mean? Maybe this might give us some insight what it is. Okay, and I'm going to call this G0 for the heck of it. And so here's the numbers. Again, they're just they're some weird fractions. My notice though, well, actually, I continue on the next page. Yeah, here I calculated the formula for way out, and I kept going and going and going. So here, the coefficient of z to the 12th, z to the 14th, and the previous numbers I recognize as powers of 2, like 2, 6, 2, 1, 4, 4. I've seen that number before, but I don't know this one so well. 3, 3, 5, 5, 4, 4, 3, 2. So I factored it, and it turned out that's 2 to the 25th. And so this gives me pretty good evidence that all the denominators in this formula are powers of 2. And that turns out not hard to prove with number 3. Okay, so now, anyway, I got this long formula for the square root of the 3/2 area guy. And now I'm going to do the same thing, but I'm going to change z to minus z in the formula. So where the previous one started out 1 plus z over 2 plus 3/2 z squared and so on, the new one starts out 1 minus z over 2 plus 3/2 then minus. So all the odd powers of z now have a minus sign, where previously they had a plus sign. That's the difference between G1 and G0. And so here we got these two generating functions which represent who knows what, a half of a 3/2 area tree. But we have two of them, one that has minus signs in it and one has plus signs in it. So let's see what happens if we take the product. We multiply the two things together. Look at that, all integers. All those fractions cancel out, and we're just left with nothing but integers. Not only that, look at the integers. 1, 2, 1, 1, 3, 12, 55, speed limit. This is the ternary tree. For some reason, I put together two of these half guys, and one with the square root, with the minus z and one with the plus z, with all kind of fractions in there, and I got ternary trees out of it. Okay, well, that was the product of the two. Let's try the difference. 1, 2, 7, 30, 143. This is the square of the ternary tree function. That's the other sequence that I said is going to be one of our favorites tonight. Okay, so it looks like we've got a conjecture here that, I've only calculated out the first 10 coefficients or so, but all those fractions cancel out. It can't just be a pattern. So when I saw this, I said, whoa, wait a minute. This b3/2 has to be a much more interesting function than I ever thought before. Okay. Now, in order to understand this connection, then I'm going to go back to ternary trees and start thinking more about ternary trees. So remind you about ternary trees. Let's see, a ternary tree can be understood if I draw you a random one here. So let me do one that has 6 nodes, and I'll give it 3 non-trivial ones at the root, and then I'll put one here as the middle child, and here I'll put one as the right-hand child, and then so this guy has an empty left child. This guy has empty left and middle. This one has empty all 3, and so does this one. And I can number these, so I'm going to call this, wait a minute, this guy also has to have his 3. Kids, okay, so there's 6 nodes, and then there are 13 of these hangers-on that represent empty ternary trees, and I'll number those 0 through 12. And then I'm going to number the nodes themselves in what we call post order, which means you come to this guy first, and then this guy, and then this guy, and this guy, this guy. This is the post order of walking through a tree. And so anyway, that's a ternary tree. Now, computer scientists know that that trees correspond to evaluating algebraic expressions, and we often do that with a stack. And so if we think of this expression evaluating it, we say we sort of put numbers in place of these boxes here, and then whenever we do a ternary operation, we combine the 3 numbers that we've got, and so. If we do that, we put numbers on the stack one at a time, and the size of the stack after we put 0 on this thing, we got 1 guy on the stack. Then we put 1 on, and I got another guy on the stack. You see the number 1 here. If I put 2 on and 3 on, then I've got 4 guys on the stack. And now we evaluate this ternary operation. So we replace the top 3 guys on the stack by A. And so I drew a little red line here. It says now the stack went from 4 down to 2, and I've got A is sitting here, and then 0 and 1 are still. Sorry, 0 is still sitting here too. So A and 0 are the 2 guys on the stack. Then we put 4 on the stack, and we evaluate B. So then B is sitting there as the only guy on the stack, and so on. Every time we encounter one of these square boxes, we add it to the stack. Whenever we encounter a round node, a ternary operation, we remove 3 guys from the stack and put the round node on in place of it, so the net is the stack went down by 2. And so what we have here is a path that consists of steps that are either +1 or -2. And the number well, the first step is always a plus, but the number of ways to get back to something where there's only 1 on the stack after a certain number of steps is equal to the number of ternary trees. Every ternary tree with 6 nodes would correspond to another path that goes from here to here. It would have the right number of +1s and the right number of -2s, and the main thing is it never goes down to 0. The stack never gets empty. The stack always has at least 1 guy on it after we put 0 on there. So that's a connection. Then the ternary trees is also equivalent to paths on this in a random walk that has steps of size +1 or -2. And so now I got to show you a great paper about such random walks. This was published 2002, Theoretical Computer Science. And I mention it because I had the privilege of meeting Cyril Bender in June when I was in Paris to give a lecture in honor of Philippe Flageolet, who unfortunately died a few years ago. I hadn't read this paper before. I knew it existed, but I didn't know what a beautiful paper was until later. And in this paper, they talk about the four kinds of walks that are they're generally studied. First is an arbitrary walk or a path, which says that you have steps of different possible kinds of steps. In this case, they're showing lots of different kinds, but in my case, I was only considering +1, -2. So an arbitrary thing is called a walk. But if it comes back to 0 at the end, it's called a bridge. Like a Brownian bridge or something like this. And then a meander is a walk that never goes below 0. And an excursion is a meander that ends up at 0. So these are the four kinds of walks that are studied, and each of them has great algebraic techniques to understand how many there are of that kind. Okay, now, so I'm going to now try to study meanders with steps that are +1 and -2, and I'm going to call it the generating function. I'm going to call it f of z and u, where z is going to count the length of the path, and u is going to count the height. And so the coefficient of z to the j, u to the k is going to be the number of meanders of length j that end up k steps above 0. And so if it starts out with the empty meander, and then there's zu is a meander of length 1, and we're one step above. Do you have a question? Okay, and then length 2, we're at position 1. We can't go down to -1, so we have to go up again. So the only possibility after 2 steps is to be at height 2. But at 3 steps we have two chances. We have 2 choices, and it's 1 plus u cubed, because we can either come down to 0 or go up to 3. On this step, okay? Now, what about 4 steps? If we're at 0, then we have to go up. But if we're at 3, we can come down to 1 or go up to 4. So that gives us actually 2u plus u to the 4th. With me, there are two ways to get to 2. One of them come up from 1, the other come down from 3. And z to the 5th, what happens now? Well, how many ways to get to 2? There's going to be something in front of u squared. Any guesses? What? 2, 5, 83. Okay, so I can get, after 4 steps, I'm either at 1 or 4. So now I'm either going to go to 2 or 6, because I'm either adding 1 or subtracting 1. So if I add 1 in this case, then I get 2 ways to get there. But if I subtract 2 from this one, so this is 3 u squared plus u to the 5th, and so on and so on. The next one, it turns out, is 3 at 0, and then 4 ways u cubed, and then u to the 6th, and so on and so on. Now, it gets easier if I use shorthand to do the calc. I mean, if I write the coefficients out without the z's and w's and u's. So let me just write it it's polynomial of the case where where z is 0, the polynomial is just 1. When z is 1, 0, 1 corresponds to u plus 0. Z squared is 0, 0, 1. Z cubed is 1, 0, 0, 1. This is 1 plus u cubed. 1 plus no u's, no u squared, 1, and u cubed. Then I get 0, 2, 0, 0, 1, 0, 0, 3, 0, 0, 1, 3, 0, 0, 4, 0, 0, 1. And you see what 7, 0, 0, 5, 0, 0, 1. You can sort of see how I do this by just not exactly night moves, but I get each one by looking at the line above it and either going 1 this way or 2 that way, and I add those two numbers together, and so that gives me this expression, and so now I can let the computer do that for me, and so I have in that file that I put online. I have something that evaluates these coefficients, which I call C of P and Q, and these are called the ternary ballot numbers. And for ternary, this is ternary trees, but any kind of trees, we have the corresponding table of numbers, and this is actually, whoops, did I take the wrong volume here? This table appears in my book, The Art of Computer Programming, on volume 4A on page 790. It's one of the most used pages of my book. Again, I keep turning this. I run into another problem where I need these numbers somehow. So here we see the numbers, and I want to emphasize that these numbers are the coefficients that correspond to what I just calculated. Why is that? Well, it's tipped a little bit. You have to go this way and reflect left to right. But where I have 1, 3, 3 here, and then I have 1, 4, 7, and so on. In the book, that went 1, 3, 3, and then 1, 4, 7, 1, 5, 12, 12. So it's the same set of numbers, but just in a slight disguise. And there's formula for C, P, and Q. A couple of formulas. This is the one I like the best, actually. People usually use this one because it's a single term, but here it's a sum of two terms. Makes it much more clear that why it's an integer, because these are obviously integers. Well, this doesn't look like it has to be an integer. Okay, so that's what happens in these. That's what numbers we came up with here, and. But I want to emphasize that let's see. If you look at the extreme numbers at the end of each line here, look what we have. First, if I go the even numbered lines, I get 1, 1, 3, 12, 55. Speed limit. But if I look at the odd number, so I put a circle around these numbers. And if I look at the odd numbers and I put a square on those, that's 1, 2, 7, 30, 143. Those are the other ones, okay? So in fact, what's happening is these are numbers that are that are somehow important to our problem, right? And we know also that we have a pretty good conjecture. This means the number of ternary trees. In fact, we know it's a number of ternary trees because it's the number of because it's the coefficient of when we have when we don't have a power of u in here, that means that we're at level 0, which is the definition of being a good ternary tree, and that makes it an excursion instead of a meander. So here with the 1 and the 1 and the 3, that's just 1, 1, and 3, and those are the extreme points that I just put a circle around in my other formula. So All right. Now, these numbers, then the ternary tree numbers seem to be coming up all right, and we haven't proved it yet, but we're starting to understand the territory, and it definitely seems to have something to do with the f function. So now, let's see. Okay, so now let's remember the definition of f that I had. How did I formulate this? Well, when I had z to the j, u to the k, then that sort of mapped into, on the next step, either z to the j plus 1, u to the k minus 2, I'm sorry, u to the k plus 1, this means I added 1 to the height, or z to the j plus 1, the new step, u to the k minus 2. However, this is only allowed if k is greater than or equal to 2. If k is 0 or 1, I'm not allowed to subtract 2. So this is the rule that I used, and it says that in a sense, if I have a kind of an equilibrium situation, as in this function here, z to the j, u to the k minus z to the j plus 1, u to the k plus 1 minus z to the j plus 1, whoops, z to the j plus 1, u to the k minus 2, is somehow usually 0, the coefficient of these things. If in f is usually 0, this is z to the, I mean, whenever I have a coefficient in front of this guy, then the same thing has been added to the other guys. So this is z to the j u minus 2 times a polynomial here is u cubed minus z u cubed minus z. And this polynomial is going to be a key to understanding the function f, because if we multiply f by this polynomial, we're going to get mostly zeros. We're going to annihilate all the stuff. Okay, now that's not hard to see if we look at it in the following way. So let's suppose remember f of z and u is this big sum of all the number of ways to z's and u's with different powers with, and it starts out as 1. And then we take f of z and u and multiply it by z times u plus 1 over u squared. This means, in other words, we take every term of f that we had and we multiply it by zu. That means go up one step. And that, we also might multiply it by z over u squared. That means go down 2. When z goes up 1, u goes down by 2. However, then we have to subtract out the cases where we weren't allowed to go down 2. So I subtract out, that's a function of z, that's a generating function of z divided by u squared. This is the case where I was at height 0, and I want to go down, and then I also have to subtract off the case where I was at height 1 and wanted to go down by 1. Okay, so this it is a way, if I got two unknown functions here, a of z and b of z, but if I knew what they were, that would express what this function f is, and f is the function I'm trying to determine. And so what this means is that if I can rewrite that formula this way. I'm doing it in a slightly tricky way, but you can easily check it with algebra. So I brought this term over to the left, and I multiplied it by this guy. This, and multiplied everything by u squared, and so this is u squared minus b of z u minus a of z. So this is a function. This is an identity. F is unknown. A is unknown, B is unknown. How am I going to solve this equation? However, it turns out that there's a beautiful way to solve this equation called the kernel method, and that's what I'm going to explain next. So F represents all these meanders, and A represents all the ones that end at 0. In fact, I can write it down. What's A of Z? It turns out A of Z over Z is the coefficient of u to the 0 of f of zu. This is the case where I wanted to multiply by z over u squared, but I couldn't. This is 1 plus z cubed plus 3z squared, 6, and so on. B of z over z is the coefficient of u to the first power in f of z and u. And so if I look at the case, you see where u to the first power occurs, I get a z here, and then I get a 2z to the fourth there, and I get what's going to turn out to be 7z to the seventh, and so on. And our conjecture actually boils down to the fact that this is equal to t of z cubed, and this is z times t of z cubed squared. This is the number. The next number here is going to be 30. The next number here is going to be 13, and then 20, 55. These are the cases where when I was forming this thing, I had trouble because I couldn't fall off the left-hand side here. When I formed this table, I wasn't allowed to go. So these are the numbers 1, 3, and so on, and those are the numbers that I circled and put squares around before. Okay, so now we got this equation, and it has lots of unknowns, but we conjecture what this is. I put a question mark here, but I know probably what it's going to be. And now the right question to ask is, well, wait. Now let's take a look at this cubic polynomial here. It's linear in z, but it's cubic in u, and that's the important thing. I can solve for. I can factor this and find the roots of this polynomial. I can find the roots of this cubic polynomial and find out values of u that satisfy this. And so I'm going to factor. So what are the roots of this polynomial? Z u cubed minus u squared plus z. Okay, so you could think of z as a number like 5 or something like this, or 0.1 or epsilon. But anyway, it's a there are going to be 3 values of u, complex maybe, that satisfy this, and I should be able to express these values somehow. And it turns out that that's not hard. So I rewrite this equation: u squared equals z times 1 plus u cubed. That wasn't hard. I set this equal to 0. And so now solve for u. It's a cubic equation, but I'm not going to do it the normal way. I divide by z, and I call this r. And this is equal to 1 plus u cubed. But this is equal to 1 plus, here's the tricky part, watch this closely. U is equal to, r is equal to u squared over z. So I can write this as z to the 3 halves, r to the 3 halves. Because zr is equal to u squared, and if I take that to the 3 halves power, I get u cubed. Yeah, anyway, you don't get it, you watch it on the video afterward. And that is, is there anybody here beside Bill Gosper guesses why I'm doing this? I know that now I have shown that r is equal to 1 plus z to the 3 halves r to the 3 halves. This means r is equal to my 3 halves area function, b 3 halves of z to the 3 halves. Because the definition of this function, you know, b to the 3 halves of x is equal to 1 plus x times b to the 3 halves of x to the 3 halves power, and I plug in x equals z to the 3 halves, and I get this. So here's my, this is great. I know that I can factor this cubic polynomial in terms of my generalized binomial function here for the 3 halves area number. And this is the reason why these numbers are coming up, as we'll soon see. So now we see u is equal to the square root, or let's say plus or minus the square root of zr. R is u squared over z, so u is plus or minus zr. And so, in other words, one of the roots is going to be, for example, the square root of z times b 3 halves of z to the 3 halves to the 1/2 power, because I have to take the square root of it. Okay, well, back to Mathematica, I can calculate that guy, and it turns out here it is. Wait a minute, nope, I'm the wrong one. Let's see. I didn't do that yet. Okay. Well, somewhere I thought I calculated the 1/2 power of this guy, but well, yeah, we had that way back. I had the b. That was G0. And I took this function out to 16 terms, and I took the square root of it, so these are the numbers that I'm getting here: 1, 1/2, 5/8, and so on. Now I'm taking this, I'm plugging in z to the 3 halves, and I'm multiplying everything by the square root of z. But that's the same function I'm getting here. So it's essentially g of G0, but with a little bit of rescaling. And then the G1 that we calculated is also a root, and so in that case we use the negative square root here, and I sort of take b 3 halves of the other 3 halves power here, and that's what happens if you sort of change z to minus z. You get the other root of this equation, and so it turns out then that I know 2 of the roots. I know 2 of the 3 roots of this equation, and so I call this u1, u0, and this is u1. Now I can get the third root in the same way, and I'll do that almost the same way, and I'll show you that one too. Watch this for the third root. Instead of taking u squared over z, I'm trying to solve this equation. This time I take 1 over zu. And so I divided this expression by zu cubed. And so on the right-hand side, I get 1 over u cubed plus 1. I call that s. And on the right-hand side, this is 1 plus z cubed s cubed. 1 over u cubed is equal to z cubed s cubed. And therefore, s is equal to what? b3 of z cubed. This is the relation that defines the ternary tree function. S is 1 plus something times the cube of s. And therefore, you see I have u is equal to, the root is then 1 over zs, and so that's the third root. u2 is equal to 1 over z times t of times b3 of z cubed. So now I've got a, I know all three roots of that guy, and in order to prove it, I will, I calculated that to show you, and that's number where, okay, so here I have the three roots. The first one is called, in my notation of this file, it's called T21, 15 terms with a 0 for the first branch and 1 for the second branch. And the third one is 1 over the case for 1, 2 with the 0th branch. It turns out that you multiply that together, and sure enough, you get exactly what we wanted. I divided by z instead of. I mean, these are the product of the three roots. So we factored out that equation, and it worked great. Okay, now this actually it proves one of my conjectures, because it says that if we have u minus u0, u minus u1, these are the two things I called G0 and G1 before, and I had conjectures about those. And it turns out that my conjecture was essentially that was equal to u squared minus u z squared t squared minus zt. What I mean is, if you look at this, the product of u0, u1, that was the first miracle where I multiplied those two numbers together, and I got the ternary function. So that's this coefficient. The other one was the sum of these two guys. Well, it's actually the difference because I had the sign different. But there's where I got the square of the ternary numbers coming in, and so this is a conjecture that I would like to show. But now if I multiply this by u minus 1 over t, in all cases t is the function for ternary trees with z replaced now by z cubed. I multiply this together, and what do I get? I get z, sorry, let me sorry. Here I have z times, yeah, that's supposed to be the thing I multiplied there together. So let's see what we get. We get u cubed minus u squared. The coefficient of u squared is z squared t squared, and then plus 1 over t. And then I get minus zu. What?
Minus 1 over t, we think.
Well, I have a minus here.
Oh, good, thank you.
But,
sorry.
Yeah. So I had minus and minus, and okay. Then when I get to u itself, I've got a z squared t. So nope, I got a zt here. Zt, and so let's see. Zt minus zt I'm supposed to get. Minus zt. Yeah, there's a minus zt from this, and here's a minus zt from here, because this is 1 over t with that one. Yeah, minus. So this term goes out, and then the constant term is plus z. And what about this term here? I'm sorry. This term is. This is t cubed, I got something mistaken here. 2, 1 over t. Okay, let's see. Start over. I'm going to u squared minus u z squared t squared minus zt. That's what I got for the first part. Now I'm going to multiply by an extra z in here, and then I get a z over t here. That makes it that clears some of the z's. But I just multiplied that last term by a z. So now I get zu cubed here, and then I get minus u squared, and here I get z cubed t squared plus 1 over t. Then I get a plus u, and I get z squared t minus z squared t, which goes out, and then I get a plus z. This times that, z squared. Something's fishy.
I don't see why you don't have a z squared t in the result for u.
What, here?
No, upstairs.
Here,
Previous page,
the previous page.
right there. Z squared t squared divided by t.
Okay, let me think now. Oh, this was part of my problem that I had. I forgot the z here. Because u1 is 1 over zs, and I only wrote s. That's the problem. Yeah, I'm sorry. I forgot this z here. So the third root is 1 over z times t. And that explains the whole business. So now this goes away to 1 over t. Everything is going to work now. It's going to come out to it's going to be z at the end. So zu cubed, except I have really I wanted minus u squared, but that's okay because z cubed t squared plus 1 over t is equal to 1. That's the same as saying z cubed t cubed plus 1 is equal to t, which is the definition we had. Okay, so plus z. So anyway, this proves the conjecture that we had. We knew it was true because all those numbers were checking out. But anyway, that's it. But now we really haven't tied that in with the meanders. I only tied it in with the roots of this equation. And so here's the final punchline there, and that is the important part of the kernel method. So I had this equation, which I'll rewrite, minus z cubed minus u cubed plus z f of zu on the left-hand side. There was one unknown. On the right-hand side, we had this equation, b of zu minus a of z. And now here's the point. I can plug in u0 u equals u0 on the left-hand side, and I get 0 on the left because this is a root of this guy. I can also plug in u1 on the left, and I get 0 on the left. And so these are two roots of the right-hand side. The right-hand side is a polynomial in u. It's a quadratic polynomial this time, not a cubic. So in other words, this right-hand side has to be equal to u minus u0 times u minus u1. It's the only, you got the two roots. And so therefore, the a and b are actually tied with these numbers. The numbers in this equation are the a and b that I got from the meander problem. The ones I got the other case were the a and b that I got by my conjecture. Anyway, so in order to show you now what we've done, I'm going to work a little bit harder problem, but the methods are going to be the same. So I'm going to run through it so that you can check it on the web if you see, because this is really the beauty. This is really the clincher. Now instead of using ternary trees and steps of size +1 and -2, I'm now going to consider steps of size +2 and -3. So now we're going to do meanders, but every time we either go up by 2 or -3. People think of this as say a club where people can come come in, and at the beginning of the day nobody's there, and at the end of the day everybody's gone home. But meanwhile, people come in pairs, but they always leave in threes. It turns out there's a designated driver and two other people, when they leave. And so we want to know how many ways are there for people to go in and out of this club at the end of the day, having had so many transactions, and this is an interesting generating function. So we can start it out, and we get f of zu before. This time it turns out to be zu squared. The first step, after one step, we have two guys in there. After two steps, it's we always have to have four people in there. After three steps, however, it's either 1 or 6, because we either subtract 3 or add 2, and so on and so on. And we start looking at the coefficients that we get, just as I did before, and we get a pattern like this. And so on. We get a bunch of numbers by this shift over 2 or shift over 3 rule, and we get a table of numbers that looks like this. And the table of numbers can be interpreted in the following way. Actually, I have a chart I forgot to show you for the ternary case. Here we have a graph where I've shown connections between. It's a grid with parts suppressed, and I'm saying how many paths are there from the starting point to a given point. And there are 143 paths from here to here, and the reason is that 55 of them go to here and 88 of them come to here. And these 88, 55 here, and 33 here, and so on. So you just easily construct this. If you have any kind of a grid, you can figure out how many ways there are to get from one place to another. And in the new problem, the numbers that I'm getting are these for the steps of 2 and minus 3. And again, it's paths in a grid, and I'm getting key numbers here that are looking like 1, 1. Actually, I'm getting three kinds of key numbers. So I'll put a circle around these, every third one. 1, 2, 23, and 377, and then I'll put a square around the next guy, or let's put a triangle around it. So that's 1, 5, 66. And there will be some guy down here, and then there's another one here, which I can use a box, a diamond. Okay, so that's 1, 9, 136, and so on. It'll be over here. So these are the extreme numbers that are the cases where corresponding to A of z and B of z before. These are the cases where we want to subtract 3, but we can't because we're too close to the origin. So we get 3 power series in this case, not 2. And what are those power series? A, z, B of z, and well, it turns out they. We have to factor a polynomial, and the polynomial is z u to the 5th minus u cubed plus z. And this has 5 factors, u minus u0, u minus u1, u minus u2, and then it's square root of z u minus square root of z u3, and square root of z u minus square root of z u4, where u0, 1, and 2 are equal to z to the 1/3 times the generalized binomial of z to the 5/3 to the 1/3 power, and u4 and 5 are 1 over z to the 1/2 b b of 5 halves of z to the 5 halves to the 1 half. In other words, here I have another example of fractional 5/3 area trees, 5/2 area trees, and I get 3 of these because I choose 3 different cube roots of z here, and I get 2 here because I choose 2 different square roots. So when you multiply these terms together, it turns out that you get all integer coefficients. I mean, all the coefficients go away, and you multiply these two together, again you get all integer coefficients. All the fractions disappear. The numbers that you get are the numbers that appear in the extremes of this problem, and the numbers that you get in the other case are the numbers that you get in the extremes of the problem where you had -3 and +2 instead of, I'm sorry, +3 and -2 instead of +2 and -3, because you consider a club, the people, you consider time reversal, people come in 3s and leave in 2s. It's the same number of scenarios except in the reverse order. So anyway, this is the the fascinating theory of, and I've run out of time, so I just show you what else is on the transcript that you'll see on the web. There's a that particular problem is discussed in the paper by Van der Aa and Flageolet, and they show the pattern of numbers there, and then they say, now here's the number of scenarios for the club. It's either 2, 23, and these numbers are the so-called Duchamp numbers. And Duchamp is a person that I have not met. However, he wrote a very interesting paper discussing this particular problem, and he had a completely different formula for those numbers that he derived by using context-free grammar. And what he does is he takes, he gets it as the sum of these binomial coefficients here, which are not even easy to believe are integers. In fact, in order to prove that they're integers, I have his formula here. Go up, yeah. Let's zoom in this. This is the binomial of 5n plus 2k, choose k, and so on and so on, and divided by 5n plus k. So this is I call it Duchamp term, of n and k, and it's product of binomial coefficient divided by something, and he claims it's an integer, but it's not at all easy to prove. Now here I found another formula which explains why it's an integer, because I write it as a sum of 4 terms, each of which is obviously an integer, and call that alt Duchamp term, okay? And then Duchamp number is the sum of the Duchamp terms from k equals 0 to n, and so here's Duchamp's paper, right? And I showed, I found a reason why it's an integer, and also then I now can calculate with my scenario. On the transcript, I calculated the Duchamp. Well, I didn't show you the Duchamp term. Oh, okay. Well, anyway, you can play with it and try lots of n's and k's, and you'll see that they do actually check out to be equal, and so it comes out that his formula does work. Now there was another paper that these guys were unaware of that was published in an obscure journal called the Journal of the Institute of Actuaries in 1954. And that is not in Stanford's library, but I checked it out and got it from Berkeley Library. This was before the state of California ran out of library budget. 1954. They had and it's a paper, amazing paper by a guy named Michael Terence Lewis Bisley, and here's the title of his paper. It turns out that he actually discusses the Duchon numbers in his paper, and he has a completely different formula for the numbers, which has nothing to do with these polynomials I've been showing you at all, and that's the Bisley formula, which is the exponential of a sum of binomial coefficients of this form. Rather simple formula. And so if I had more time, I would explain to you why that works. But in fact, the reason is something about the generalized binomial coefficients that I didn't know before, and it qualifies as a brand new theorem about trees, I think. And that is something that I just added to. So the next printing of Concrete Mathematics is going to have a new graffito in the margin of page 201. It says, "News flash, the natural log of script b sub t has actually this really simple formula, binomial coefficient tk over k divided by z to the k over tk." And you know, all my life I've been playing with Catalan numbers. Even when t equals 2, I didn't know this formula for the logarithm of the Catalan number. I showed it to people who are specialists in this, and it was new to them. And then an hour after I reached them, I found it in my own book. So I turned to volume 2, and there's an exercise in one of the darker corners there. On page 535, I have a formula, and I didn't know, you know, when I answered this formula, that's what is exercise 22. It says that I said, well, you know, anytime we have a generalized function like this, like its logarithm also is going to be pretty nice. And so so I found out to my surprise that I could have known this formula years ago. I guess to summarize then, there's still new things under the sun, and amazing coincidences out there, beautiful patterns and numbers that bring together things that you would never think were connected. If I had more time, I would show you application to probability. It turns out that you can use the 3/2. I'll just give you one hint of it. Consider p times q to the 1/2. This is p is a probability, and q is equal to 1 minus p. And in general, I'm going to be interested in p to the a, q to the b. And as p goes from 0 to 1, this goes up and then goes down. Because when p is 0, it's 0, and p is 1, it's 0. And so at every point here, except at that extreme where the double root, there are two values. That p to the a, q to the b is also equal to p hat to the a, q hat to the b for some p hat. You give me p, and I can, you know, then p hat is going to be a mate, and its corresponding 1 minus p hat is going to have the same value of here. So there's this interesting mirror relation, and it turns out that I have a formula that will calculate p hat in terms of the b to 3/2 function. That's illustrated at the very end of these. At the end here, let's see, I'm out. This is a little out of order here, but I calculate the p hat when p is 0.3, and I get this number 0.367. Sorry, it took a while to compute the function. Mathematica was reading input before it got this answer. Okay, so then I input and I asked for the hat of this guy, which was 0.3 again. And then I asked for the same thing, the mate to 0.7 and the inverse mate. So the formula for calculating these P's and Q's is in the Mathematica file that I gave you, and it shows that there's an easy way to solve this probability problem as well. Okay, Merry Christmas to all.